The next thing to do is address decoding. What I'm going to try first is to use a 74LS138 1 to 8 decoder. This is a common way to do simple address decoding. The high 3 address lines A13 through A15 get decoded into 8 blocks of 8K bytes, and in this case the E clock gates the chip selects for the right timing. I'm not going to use the low address lines yet, but since they will probably cause all the port C LEDs to turn on, I'll remove the LEDs first. Now I'll add the 74LS138. So when it first starts up in single chip mode, the port B outputs are floating high, which selects output 7. And the 74LS138 just gates it with the E clock. Currently, the H prior register at 3C is set to 05. The low bits have to do with interrupt priority and are not important here. 4 high bits are RBoot, which enables the boot ROM, but it's only ever set by starting in the bootstrap mode or special test mode, SMOD, which starts as the inverse of mod B, MDA, which starts as the same as mod A, and IRV-NE, where IRV stands for internal read visibility, allowing internal memory accesses to show on the external bus. Changing H prio from 05 to 25 sets mode A, activating expanded bus mode. The other 6 outputs aren't doing anything, but if I look at output 1 and try to access its address block, I will see a select pulse. Trying a different address block doesn't affect output 1. But if I look at output 2, now you can see it. Now I need to add the low address latch. Usually a 74LS373 is used for this, but on a breadboard the 74LS573 is better. It has the same function, only with a different pinout. It almost drops right in where I had that LED board, needing only minor changes. And here's a schematic of where it is now. Or it would be, except that I got the LS573 backwards. With pin 1 in the same direction, it puts both outputs together. So I had to flip it around. Oops. I went ahead and added a RAM chip because I couldn't wait. That's quite a mess. There, that's a little better. I have the chip select connected to the second output of the LS138 for 2000 through 2FFF. When I try to see what's in there in single chip mode, you can see that nothing is there. After enabling extended bus mode, you can see that there is data there. So what happens if you put it on the same page as RAM or ROM? Move this to 0. I can still see that there, but now if I move it back, you can see that it got written to with the memory command here. What happens is that internal memory and registers take priority when reading, but the external bus causes writes to go to both internal and external memory. And this shows the other mistake I made when wiring up the RAM chip. Note that 2000 and 2100 have the same data. That's because instead of connecting A8, A9, and A10, I connected those three inputs to A9, A10, and A11. Oops. Now you can see that 2100 has different data instead of repeating 2000. So here's what the schematic looks like now. I'd like to use a 32K RAM chip, so instead of using the 74LS138 for decoding, it will just use A15 low as its chip select. This will map it to addresses 0 through 7FFF. And now I've got the 32K RAM working. I did have to make one change. The output enable was previously on not RW, but the timing was flaky. I moved it to not E, and now it's working much better. Now I've added an EEPROM to it. I also took some time to tidy up the reset button and the serial board. The EEPROM was programmed with the same code as is inside the 68HC11 chip, except that I've changed the dash in the startup message to an equals. Now when I start up with both mod A and mod B off, it starts in expanded bus mode and runs from the EEPROM at F1000. However, in this mode, the existing Buffalo ROM from the 68HC11 is still present at 7000. In order to make it go away, I have to store 4 into the config register at 3F to clear the ROM on bit. And here's the schematic again with the EEPROM added. I also made a third prototype because I wanted to see if I could route the wires a little better. I also made this one use a bare crystal. That was more troublesome than I expected because it really needed the 10 megohm resistor and the little capacitors to run properly. If you have the choice between using a bare crystal and a CAN oscillator, go with the CAN. It's much easier to use. Then I tried one more thing. I wanted to see if I could have the RAM duplicated in the upper and lower half of the address space. I was hoping that would be an easy way for the interrupt vectors to be in RAM. So instead of using A15 as the RAM chip select, I just grounded it. Then I tried copying all 4K of ROM into it, then copying it back. Even though it's ROM, it would only notice if the data wasn't the same. But on both units, it would make errors copying either way, often at the same addresses. When I put the chip select back to A15, there was no error. Swapping out the RAM chip for a faster one didn't help. So what's next? I need to come up with some code in EEPROM that will let me start up with 32K of RAM, a full 0 page, and the interrupt vectors pointing to RAM outside the 0 page. I can't move the interrupt vectors or I/O register page with Buffalo running, but for now I should be able to use it to load code into RAM so that I can work on a boot ROM.